I already posted 2 videos about these 2 boards connections. Why did I mention this again? And what happened with the former setup? Hi, welcome to Slow Engineering. I'm David. In the previous video, I demonstrated that the PWM signal ground of the SKR3 board has a different voltage level than the driver ground. Therefore, it is not advisable to directly connect the 2 boards. To resolve this issue, I presented a solution involving a 790A isolation amplifier and a boost module to increase the voltage to 5 volt. The solutions were fine initially as the PWM signal was converted into RPM speed. However, when I analyzed the data, I noticed the spindle was unstable. Upon further investigation, I discovered that the spindle was not spinning continuously, which caused the tachometer to provide varying readings with a significant deviation. I then reviewed all my steps and adjusted the firmware to RPM-based control. After examining the setup, I noticed that the boost module has a minimum voltage requirement to boost to a higher voltage. Despite this issue, the spindle rotates even when the PWM signal is set to 1. Therefore, I suspected the problem might originate from the 790A amplifier. In this situation, the amplifier is an isolation device, producing 0 or 2.5 volt as PWM signals. However, a PWM signal may not be suitable for direct connections to the voltage control on the DC driver board. I acquired another PWM to voltage module for testing to confirm my assumption. Before implementing it into the system, I thoroughly evaluated the module. Upon inspection, I discovered that all the ground pins on the board were interconnected. This was problematic as it was incompatible with the scenario involving 2 distinct ground level boards. As a solution, I modified the isolator input side to separate the ground pins from the others. The module can handle an input of 0 to 10 volt or 12 to 24 volt, and outputs at a range of 0 to 10 volt based on the PWM duty cycle. This newly modified isolators converts the PWM signals to the range of 0 to 10 volt. The output is connected to the DC driver, producing a more consistent spinning sound. However, the PWM range is limited, as the DC driver board can only accept a maximum of 5 volt, which is only half of the available PWM signal that can be applied. I have included a line chart that depicts the voltage from the SKR3 board and the PWM to voltage module output voltage based on the PWM values. You may notice that both curves initially appear flat due to the internal circuits within the SKR3. After achieving a stable result, I conducted additional experiments to determine how to maintain a consistent speed using a full-range PWM signal. I also connected the voltage to PWM converter to a PWM to voltage module. The output range from 0 to 10 volt and is translated back into a PWM signals with a peak of 5 volt. However, non-continuous noise reoccurred. This issue confirms that using the PWM signal to replace a variable resistor for voltage control is inappropriate. The frequent high and low levels change results in unstable spindle speed control. I recently obtained an optocoupler module to help isolate and transmit the PWM signal for an apparent solution. However, this optocoupler inverts the signal, resulting in a different curve and a less linear SKR3 output. This curve could negatively impact further setup output, which is unacceptable. To resolve the issue, I modified the isolation module by removing the resistor at the VCC side and reconnecting it between the signal and the ground. This effectively disabled the signal inverting, allowing the PWM signal to pass through the isolation module directly. After testing the isolator between the mainboard and the DC driver, I found a non-continuous speed again. Based on the evidence, I realized that keeping continuous voltage stability for the DC driver was crucial. I got another PWM to voltage module that outputs from 0 to 5 volt. Once this was implemented, the spindle achieved stable rotation. This was the ideal time to remeasure the speed and switch to speed control instead of PWM. By using linear regression to process the raw data, it was possible to convert the readings into RPM. Recording speed and feed rates for different materials and tools become easier with accurate RPM control. I have conducted various tests to evaluate the connection between these two boards. If you encounter similar issues, I hope my findings provide helpful insights. If you find this video informative, please like, share, and subscribe to my channel for more project updates in the future. You can also support my projects by becoming a Patreon member. Thank you for watching, and I'll see you next time.